Myself Muniraju Naidu, Assistant Professor, Department of Computer Science and Engineering, working at Institute of Aeronautical Engineering, Hyderabad. So in this video, I am going to discuss about process synchronization in operating systems. So from the previous videos, already discussed that CPU scheduling algorithms. So what are the various CPU scheduling algorithms, right? So now in this video, I'm going to discuss about process synchronization. So what is meant by process synchronization? What is the importance of process synchronization? And what is meant by semaphores? What is the purpose of semaphores? How you implement semaphores? Now look at this, the process synchronization. This is the overview. So what is the introduction about process synchronization and critical section problem? The solution for that critical section problem is Peterson solution, and synchronization hardware, semaphores, and various classic problems of synchronization monitors and synchronization examples. So in this video, we are going to see about critical section problem, Peterson solution, synchronization hardware, and semaphores. So what are the basic objectives of process synchronization? So we know here we need to introduce CSP, that is a critical section problem, whose solutions can be used to ensure the consistency of shared data. So first of all, why we need to have this process synchronization? So in general, most of the real-time applications which requires some shared data or some shared space or shared memory locations or shared any resources. So among those situations here, there exists some consistency of that particular shared data. So for that, here we need to provide this process synchronization. So to present both software and hardware solutions of the critical section problem. So what is the background regarding this process synchronization? So the concurrent access to shared data may result in data inconsistency. So automatically we need to maintain data consistency, which requires mechanisms to ensure the orderly execution of cooperating processes. So we know what is meant by cooperating processes, right? So more than one process can at a time access the shared common data. So then you have to maintain some data consistency, which requires mechanisms to ensure the orderly execution of cooperating processes. So let us take an example. Suppose that we want to provide a solution to the consumer producer problem. So we know consumer producer problem, right? So first of all, the consumer, whenever some goods, n number of goods are consumed, then automatically the producer produces the same n number of products, right? So that fills all the buffers. So what happens here, we can do so by having an integer count. So based upon this, both the consumer and producers, we can call as a consumes as well as the produce the items. So the integer count that keeps track of number of full buffers. So initially the count is set to 0. So initially the count is set to 0. So what happens when that particular goods are consumed, then automatically it is incremented by the producer after it produces a new buffer and is decremented by the consumer. Decremented by the consumer and incremented by the producer. So based upon this introduction, here we move to the critical section problem. Critical section problem. See, let us take any real-time applications which require some n number of processors. So we don't know exactly how many number of processors are executing on that particular system at that particular point of time. So consider a system of n processors. Those are P0, P1, P2 and so on up to the Pn minus 1. So let us take n number of processors. So each and every process has a critical section segment of code. Each and every process has some critical section segment of code. What does that mean? Critical section. See, whatever the processes may be changing common variables, then updating any data tables and writing files, etc. At that time, whenever one process in critical section, then no other process may be in its critical section. Right? So, n number of processes can access at a time any common data like common variables, or n number of processes at a time can input the data to the already existing tables. So in those scenarios, whenever one process is already writing something or reading something, so that means you can call as a whenever any process, one process in its critical section, then no other process may be in its critical section. So this critical section problem is to design protocol to solve various problems. So in case of critical section problem, each and every process must ask permission to enter into its critical section. So that is described here as a entry section. Entry section. So we know the default principle of any process in case of operating system. Whenever any process needs some resources, then automatically, first of all, the particular process sends a request. Then if the resource is free, then resource is allocated to the process, then automatically the process use that particular resource. So we can call it as a request use, and finally our completion of work is done, then release. Request use release. So in the same fashion, here each and every process must ask some permission to enter into its critical section, that is described in entry section. Automatically it follows some critical section with exit section and then reminder section. So basically the critical section problem, which consists of three sections: entry section, exit section and reminder section. Right? So this particular critical section, the general structure of any particular process. Let us take, if you take n number of processes, for example, the process PI. So this is the general structure of any process. See, first of all, do, then this is the entry section, critical section, exit section, reminder section. So this is a do while loop. Right? So this is the general structure of any typical process: do, entry section, critical section, exit section, reminder section. See, I can say one a simple example with this critical section problem. So just like our bank lockers, right? See what happens, n number of account holders are having m number of lockers. But what happens in case of that particular locker room, only one account holder can at a time may access that particular locker. Right? So once any account holder needs to access his own locker, then we can call as a one admin, or we can call as a one bank manager, which allows only one particular account holder to the locker room. Is it right? So what happens in that particular locker room, right? So we need to keep some important documents or ornaments. Is it right? So in the same way, here the operating system also allows processes only one by one. How it is? So first entry section, then critical section, exit section, reminder section. Right? See what are the solutions to that particular critical section problem. Right? See, basically these are the three assumptions: mutual exclusion, progress and bounded waiting. Right? So first one, mutual exclusion. In the sense, if any particular process is executing in its critical section, then no other processes can be executing in their critical sections. So that is a basic principle of a critical section problem. One is a mutual exclusion. If any particular process which is executing in its critical section, then automatically then no other process can be executing in their critical section. Then second one, progress. Progress. So progress in the sense, if no process is executing in its critical section and there exists some processes which is ready to enter their critical section, then the selection of the processes that will enter the critical section next cannot be postponed indefinitely. So that is the progress. So we know we have n number of processes, that is P1, P2, P3 and so on up to the Pn. Right. So what happens in that particular critical section problem? Actually, a number of processes are waiting, but only one process. Let us take P1. If P1 is successfully completed, then only the system allows P2. If P2 is successfully completed, then only P3. So like that, if no process is executing in its critical section, that means the critical section is free and there exist some processes that wish to enter their critical section. Let us take P4, P5 and so on up to the Pn. So those are ready to enter into the critical section. Then now the system chooses which process we need to enter into the critical section, either P4, P5, P6 or Pn. Then the selection of that particular processes that will enter the critical section next cannot be postponed indefinitely. So that is the progress. Then third one, bounded waiting. Bounded waiting. So we know a bound must exist on the number of times that other processes are allowed. Other processes are allowed to enter their critical sections once a process has made a request to enter into its critical section. Before that request is granted. So that is bounded waiting. So definitely a bound must exist on the number of times. Right. See, for example, let us take the same example. If P1 is ready to enter into the critical section, right? See, once the P1 is ready to enter into the critical section, then at the same time some other process made a request to enter into its critical section before that request is granted, right? So that is from the process P1 sends a request to the processor or operating system. I am ready to enter into its my critical section. So what happens once the request transferred from process to the system, right? So meanwhile, that means that still the system doesn't respond to that particular request. At the same time, some other process made a request to enter into the critical section. So that is a bounded waiting. Assume that each and every process executes at a nano-zero speed. Right. So here the no assumption concerning relative speed of the n number of processes, because in real-time applications there are n number of processes. So we don't know, that is no assumption is concerning relative speed of the n number of processes. So for this particular critical section problem, we have Peterson solution. Peterson's solution. Right. So this particular Peterson's solution is a two process solution. Let us assume that here load and store are the instructions, those are atomic. That is atomic in the sense that can't be interrupted. Load and store. So what happens, the two processes which share the two variables, right? What are those variables? That is integer turn and boolean flag of I. So boolean flag of I. So the two processes shares the two variables, right? Integer as well as the boolean. So here the variable turn, which indicates that whose turn it is to enter into the critical section. So let us take our previous example. If two processes are ready to enter into its critical section, right? So those two processes shares these two variables, turn and flag. So the variable turn indicates now it's whose turn, either P1 or P2, whose turn it is to enter into the critical section. Then the flag array, which is used to indicate if a process is ready to enter into the critical section. That particular process is represented here, flag of I equals to true, which implies that the process Pi is ready. So here the I represents the process number Pi, P1, P2, P3 and so on. Right. So this is the algorithm for process Pi. This is algorithm for process Pi. See, do I look? So the flag of I equals to true, in the sense now this particular process, ith process, that is a Pi, ith process is ready to enter into its critical section. Then turn equals to J. So after completion of this particular ith process, it's time to the jth process to enter into its critical section. So while flag of J and turn equals to J, then it is a critical section. Else false of flag of I equals to false. Flag of I equals to false, this is a remainder section. Flag of I equals to true, this is a critical section. Flag of I equals to false, this is a remainder section. So based upon this particular algorithm for a Peterson solution for any particular process, here it proves that mutual exclusion is preserved and progress requirement is satisfied, whereas the last condition, that is a bounded waiting requirement, is met. So this is the algorithm for any particular process Pi regarding the Peterson's solution. Then coming to this next one, synchronization hardware. Synchronization hardware. See, generally any number of processors at a time can access any type of resource, like physical resources as well as the logical resources. Right? So like physical resources. So more number of processors can compete to access one shared printer. So what happens here? Many systems provide hardware support for critical section code. Many systems which provide some hardware support for critical section code. Then how we need to define the synchronization hardware? So basically we have uniprocess in the previously. So uniprocess could disable the interrupts. So which means that whatever the currently running code would execute without preemption, because there is a uniprocessor. Once any particular processor can access that particular process, then the processor executes this particular process only. After completion of this particular process only, the processor may again access some other process. That is the case scenario in case of uniprocessing systems. So currently running code would execute without any preemption. So this uniprocess generally too inefficient on multiprocessor systems. So synchronization hardware, that means the operating system using this not broadly scalable, but whatever the modern machines nowadays we are using that provide some special atomic hardware instructions. Special atomic hardware instructions. Right. So in case of modern architectures, atomic in the sense that is the non-interruptible. Right. So what happens here? Either test memory word as well as we need to set the values or swap the contents of two memory words for this particular synchronization hardware. See, this is the solution to the critical section problem using the locks. Solution to the critical section problem using locks. So here acquire lock, which means that, for example, the process P1 is getting a chance to execute, right? So automatically the P1 initial can get a lock. We can call it as acquire the lock. Then critical section. So automatically the P1 is entered into the critical section to execute its code. Finally, after completion of its work, it releases that particular lock because the processor allocates the particular lock to the next process. Then release lock, reminder section. So this is the solution to the critical section problem using the locks. Then we have another one, that is the test and set instruction. Test and set instruction. See, this particular test and set instruction that is described here, Boolean test and set instruction. So Boolean RV equals to the target true, and return that particular variable RV. So that is a test and set instruction. So what is the solution to the test and set instruction? Here we need to share a Boolean variable lock. that is initialized to the false. See, while test and set as well as at the same time it acquires the lock, then do nothing. Then automatically enters into the critical section. Initialize to false. So lock equals to false, then that is the reminder section. So this is the solution using the test and set. Then third one, swap instruction. So that is the swapping of two processes without using any particular third process. So whenever the two processes can share the same resource, then we need to describe here boolean A and boolean B, boolean temp. So A equals to B, B equals to temp. So that is the swap instruction. So that is a solution using this particular swap. See, here initially we need to share the boolean variable lock. Initially we need to share the boolean variable lock, that is initialized to the false. So what happens here, each and every process has a local boolean variable key. Each and every process has a local boolean variable key. So now initially the key equals to true. At the same time we need to perform the swap. So both lock as well as the key, that is the critical section. Else lock equals to false, then automatically the remainder section. So this is the solution using this particular swap. Then bounded waiting mutual exclusion with the test and set. Bounded waiting mutual exclusion, right? So that particular bounded waiting mutual exclusion, in the sense, if one particular process already executes in its critical section, then some other process is ready to enter into its critical section, then automatically the system can wait that particular process until the previous process releases that particular key, right? See, that is happening here. Waiting of one process, that is waiting of I, that equals to true, then key equals to true, while waiting of the particular process and key, that is the key equals to test and set lock. Similarly, waiting of I equals to false, that is enter into the critical section. So some other process, that is a j equals to I plus 1 modulo n, while j is not equals to the I and waiting of j. If j equals to I, then lock the false, or else waiting of that particular new process, that is a j equals to false, that is the remainder section. So bounded waiting mutual exclusion with test and set condition. Then coming to this semaphores. So this particular semaphore is introduced by Dijkstra. You know, Dijkstra is a mathematician, right? So that particular Dijkstra introduces this particular semaphore particularly for using this process synchronization purpose. So this is a synchronization tool that doesn't require any busy waiting. So simply say that semaphore is represented with capital S, that is a integer variable. That is a integer variable. So this particular integer variable can depends on only two operations. One is wait, another one is signal, right? So in case of semaphores, the two standard operations we can call it as a wait and signal. Wait and signal. So those are represented in the form of P of, that is a wait, and capital V with respect to the signal, right? So semaphores always can access to only two operations. Those are we can call as a two individual atomic operations. One is wait, another one is signal, right? See, wait of S, which represents that is the semaphore is decremented, while S is less than or equal to 0, then no operation is performed, then S is decremented. Else signal of S is nothing but it's ready to acquire, is ready to access, so that is incremented, yes, plus plus. So that is the semaphore. So semaphore as a general synchronization tool. That means basically these semaphores are classified into the counting semaphores and binary semaphores, right? So we know counting in the sense numbers, right? 1, 2, 3 and so on. Whereas the binary semaphores which takes the values only zeros and ones. So that's why these binary semaphores, which is also called as a mutex locks. Mutex locks. So coming to this semaphore as general synchronization tool. So here the counting semaphore is nothing but an integer value can range over an unrestricted domain. Counting semaphore is an integer value can range over an unrestricted domain. Then binary semaphore. Binary semaphore, we know binary. So integer value can range only between 0 and 1. So it is very simple to implement rather than the counting semaphore. So that's why the binary semaphore is also known as the mutex locks. So here what happens, the semaphores can implement. So there are a number of ways to implement the semaphores. So first of all, you can take into the consideration a counting semaphore, right? So can implement a counting semaphore as a binary semaphore? If yes, that provides the mutual exclusion. See here, initially the semaphore mutex, so that is initialized to the 1 because mutex are, we can call it as a mutex locks. Those are the binary semaphores, so they can use the values only zeros and ones, right? See then wait of mutex, so that is the critical section. That is the critical section. Then signal of mutex. Let us take one particular process which waits for its critical section, right? Automatically the particular process enter into the waiting state, right? Once the processor can accept that particular process, then automatically the signal of mutex, right? Then automatically it accesses that particular one and it can perform some operations. Finally, reminder section while true. So this is we can call it as a semaphore as a general synchronization tool. How these particular semaphores are implemented, right? So we know always the semaphore is an integer variable which purely depends upon the two operations. One is wait, another one is signal. So the semaphore implementation must guarantee that no two processes can execute wait as well as a signal on the same semaphore at the same time. On the same semaphore at the same time, right? So let us take for example, on one particular shared data, right? No two persons can at a time can access that particular shared data and modify that particular shared data, right? So in the same way here, no two processes can execute wait as well as the signal operations on the same semaphore at the same time. So that's why here the implementation becomes the critical section problem where both wait and signal codes are placed in the critical section. So what happens here? We have busy waiting in critical section implementation because the particular implementation part of code is very short. So automatically each and every process which is ready to access that particular critical section. So little bitty waiting if critical section is rarely occupied, right? So that is the semaphore implementation is purely depends upon the both wait as well as the signal. Then semaphore implementation with no busy waiting. Semaphore implementation with no busy waiting. So how it can be achieved? Each and every semaphore there is an associated waiting queue, definitely, because once one particular process is executing in its critical section, then at the same time some other process is ready to enter into its critical section, automatically there exists some waiting queue. So with each and every semaphore there is an associated waiting queue. So each entry in the waiting queue has two data items, right? So this is the waiting queue, right? So we have what is the value of the particular type integer. Then next one is pointer to the next record in the list. Pointer to the next record in the list. So these are the two data items, value as well as the pointer. Now this particular semaphore implementation with no busy waiting is done based upon the two operations. One is block, another one is wake up, right? So what does that mean, block? In the sense, it places the process which invokes the operation on the appropriate waiting queue, right? So let us take here for example P1, P2 and P3. Now P1, P2, P3 are blocked because it places that particular process which invoking the operation on the appropriate waiting queue. If any chance is there, then automatically the P1 is entered and it executes its critical section. Then we can say that another operation wake up. So that is remove one of the processes in the waiting queue and place it in the ready queue. So this is the ready queue. This is the waiting queue. Right? See, it's time for P1. So these are the only two operations. One is block, another one is wake up. See, always the block is which is associated to the waiting queue, whereas wake up which is associated to the ready queue. Ready queue. See, this is the semaphore implementation with no busy waiting according to the critical section problems. See here, we have only two operations: wait as well as the signal. Right? How we need to implement that particular wait? Implementation of wait of semaphore S. So that S is this is a variable. So the S value is decremented if S value is less than 0, and then this process is shifted to that particular list and then block. Similarly, signal. So signal, which is the reverse of the particular wait. So signal of semaphore S value is increments here if S value is less than or equal to 0. See what happens in case of wait, S value is less than 0, here the S value is less than or equal to 0. Then remove a process from that particular list. Right? So, so that means here we need to remove, after completion of its work, here we need to remove that particular process. Remove that particular process from that particular list. So these are the two operations like block and wake up, right? So that is a semaphore implementation with no busy waiting, right? So with this completed what is meant by process synchronization and what is the critical section problem, what is the solution for that critical section problem. What is the Peterson solution, syntax for Peterson solution, what is the synchronization hardware, and how we need to provide solution to the critical section problem using the logs, and what is a test and set instruction, solution to the test and set instruction, and swap instruction and solution using the swap instruction, and bounded waiting mutual exclusion with test and set, and what is meant by semaphore, what are the various operations of semaphores, and what are the various categories of semaphores, how we need to implement this particular semaphore, right? Semaphore implementation with no busy waiting. We have two operations, the block as well as the wake up, right? So with this, I conclude that the process synchronization, that is some part of process synchronization is completed. So in the coming video, we are going to see about the classic problems of synchronization. So that is a dining philosopher's problem, readers writers problem, producer consumer problem, right? Thank you guys for your watching.
Like, share and subscribe. Hit the bell icon for more updates.